So 5 properties of logs, and I want the whole list here. And you'll see when I'm doing examples or writing the properties, I tend to not always put log base B. It doesn't matter what the base is, these properties hold up. So if I write them with just the log or just the ln, right, it's the same as log base B, where B is just unknown. Could be a 10, could be an E, could be bit 2, right? So just because I'm using a particular log function with a particular base doesn't mean it doesn't work for every base. Okay. So we had our translation that was first. And when in doubt, I'm going to use that translation, right? B to the x equals y is equivalent to log base B of y equals x. It's that first property. If I'm working with something that's a log and I can't quite figure it out, I can convert it. We had the product quotient. And there's 3 there, right? There is log base B of n times n is log base B of m plus log base B of n. Product, there's our quotient of m divided by n. That's log base B of m minus log base B of n. I proved the first one to you. The second proof is very similar. It's very easy to do. You're not math majors, so I don't care if you bother doing it. The last one is also like a product, and that is log base B of m raised to the n is log base is n times log base B of m. That one I said I was going to kind of do somewhat of a demonstration of its validity in that if I'm just looking at log of x squared, I can use my first property to write this as log of x times x, which is log of x plus log of x, which you see that 2 log of x. So not a proof, right? It's just one particular example that shows, that makes it obvious that it worked. The proof is not difficult, but to save some time, I think this should give you some confidence that it definitely is true, right? If I have something to a power, I can write that as a bunch of products and split it all up as a bunch of sums and then gather them up. And then, of course, the sum of the terms is going to be that power, and would become the coefficient. So there's the list that we had done, and I'm adding to that list today with about 4 or 8 more pieces, and that is the inverse properties, and then the change of base. So my inverse properties are this. Because b to the x and log base b are inverses, they fall apart when they're composed, and all that's left is the input, right? So meaning if I have b raised to the log base b of x, all I get is x. Everything cancels out with each other. And log base b of b to the x is also x. So these inverse properties are going to be used all the time. Notice that in both cases, my variable is an exponent. When my variable is an exponent, we have not yet learned to solve things like this. I want it to say x equal. I don't want it to say something raised to the x equal. So I've got to get the exponent down, and these two inverse properties are exactly what I'm going to use. Why is it that I could take something and raise it to base b, or take the log base b of something? Why is it that I can do these compositions, right? Why is it that I'm allowed to do these compositions?
They're inverses?
Yeah, okay, yes, because they're inverses, but I needed something before that. I needed
one-to-one.
the one-to-one aspect. If I have things that are one-to-one, I can compose them with things that are one-to-one. And
what do you mean? What do you mean by compose?
Put one piece inside of another. So, like we used to say, well, like 5 times 2 is 10, right? Now I'm saying e to the 5 times 2 equals e to the 10. So all of a sudden now, once I have equality, I can take that equality and keep the equality by putting it into an exponential function because it's one-to-one, or a log function because it's one-to-one. I need the one-to-oneness to be able to do that. We've not done anything like that before. Like I said, there's a lot of blind following going on right now until we start practicing with these things. And we got a list of it on our paper when we're doing homework, and we're saying, okay, which one of these can I use? Which one does it look like? If it doesn't look like anything, I'm trying the translation one, right? Okay, I need finally my change of base formula. And it simply says that log base b of x is log of x over log of b, or the ln of x over the ln of b. So just a quick example there. Something we know, right? Log base 2 of 8. We know that answer is 3, correct? Right? What exponent makes 2 into 8?
3.
3. Okay. So on your calculators, I want you to do log of 8 over log of 2. And then same thing, ln of 8 over ln of 2 on your calculators. Make sure you close parenthesis there.
They're both 3.
Yep. So, this one comes in quite handy. Your calculator will do something like this, but I want it written on the paper with the change of base formula. And you'll see most of the times I'll be solving things with LNs just because I write less. I have to write 2 letters instead of 3 letters, or 3 letters and a number, right? If I use the ln function, since they all work, they all have the same properties, I can use ln function all the time, right? But at the end, I would want you to be able to write this as a single a single ln for me, right? And of course that would involve me going back to the change of base, log base 2 of 8, right? If I get to here, I want to write it as a single log, right? Because this is a lot less writing than all of this, and that's the whole thing. Trying to save keystrokes for speed of calculation. All right, there it is. There are all of my properties that I want you to know and that we're going to use, right? So it's about what, 1, 4, this was just a demonstration, 6, there's 9 of them. I'll see how much time I have left today. I might want to prove the nice question, Alejandro. So if you remember ln of 8 over 2, that translates to ln of 8 minus ln of 2. But ln of 8 over ln of 2 now is only going to translate with that log, that change of base, log base 2 of 8. They look similar, but they're different, right? You really should see that this one is an argument of 8 over 2, right? This one's an argument of 8 over 2. So the other one is ln of 8 all divided by ln of 2. Yes, and the book will try and trick you. I won't, because the only question I'm asking about this is to solve equations in 5.6. Right? We had 5.1, we had composition of functions, but I didn't ask you to really care too much about it until 5.2, when I wanted you to show that the composition of the inverse functions is x. In 5.3, we had our exponentials. In 5.4, we had our logs, right? And it's really the logs that are difficult, so I'm asking you for a sine table to find the domain of a log function. Now we're learning the properties to be able to solve equations, so that would be your third question on the test. Solve 1 or 2 log or exponential equations using these properties. Joseph, Joe, will you put this in the Discord for me? You weren't here Friday, right?
I was.
Oh, did you put it in the Discord Friday?
The PDF, right?
Yes, yes.
Yeah, I already
sorry about
posted it.
Sorry about
No
that.
problem.
Thank you. Okay, so we have our properties. We're ready to do some equations with them. Now, actually, before I do that, I should do some problems from 5.6, right? I should do some problems from 5.6. The ones in Math Excel are too easy. Will you open the book, please? So let me open the book. Give me 1 second. I was a student that tried to do every problem. I was always so worried I would get tricked up on a test by seeing something I had never seen before. It still happened, but by doing all of the problems, I kind of built up my ability to improvise a little bit and say, well, let me try this and see what happens, right? So that's the goal, is really eat the book all through Calc 2. Once you get into Calc 1, I would really suggest Shawm's outlines. Let me see if I could show one right here. So I use Shawm's outlines, especially for the linear algebra class or the diffie-Qs class for the engineers, diffie-Qs for the computer scientist, linear. And you want the linear and advanced linear. The advanced linear have all the proofs in it. So Shawm's outlines, they're pretty cheap. So here's physics, diffie-q's, right? Complex variables. You're not going to take that, but you'll take the calculus will be all Calc 1, Calc 2. Yeah, so they're pretty cheap. I have seen some that you can get free as a PDF, but just be careful. I would say download it at school first before you ruin your own computer. If you download something bad at school, they can just fix it. They can just fix the reinstall everything pretty damn quick. But at home, not so easy unless you're ready for it. So I'm just opening the textbook here to look at problems in 5.5. And of course, there's lots of examples, which is good to do. And they don't do anything like find the actual domain here, right? If you're looking at example 4, I'm going to ask you one like find that domain. What they do is cheat it and just say, let me just give you the far right interval. Let make x bigger than 1, and then everything will work out. Right? They're not actually doing that sign table to get to the domain. They're just taking the easiest route of it. So you can see here I'm dividing, right? I'm dividing x squared by x minus 1 quantity cubed. So I get 2 different log functions. Right? You with me here?
Yes.
So far, so good.
And so then I get 2 different log functions, but then I bring down my exponents. So the ln of x squared becomes 2 ln of x. The ln of x minus 1 quantity cubed, the cube comes out as a coefficient of 3. And then I'm finished. And here is the whole piece in reverse, right? Let's do log base a of 7. Let's do part A here. Log base a of 7 plus 4 times log base a of 3. Log base a of 7 plus 4 times log base a of 3. So this is my first property, right? The product one. And but I can see that I have got a coefficient. I want to tuck that in first. So log base a of 7 plus log base a of 3 to the 4th. Now 3 to the 4th is 81. So I can, anytime I can simplify things like that, I will. And now I see that I'm multiplying these 2 arguments, right? And I get a final answer of log base a, well, not final, 7 times 81. Which is what, 257? No, 567?
Yes.
And there it is. So using the properties going forward, use the properties going backward. Little strange, but you'll get used to it. And I guess part of the issue is which way do I go, right? Do I sum things up first, or do I turn them into products first, or et cetera, et cetera? And you'll learn that pretty quickly. So let me change. There's a proof of the change of base formula if you're interested. But let's just look at one really quick. Change of base. And then we can move on. So I know 2 squared is 4, right? I know 2 cubed is 8. The question is, what do I get for 2 to the x equals 5. And I just picked the 5 because I wanted the answer to be between 4 and 8. I could have picked 6, I could have picked 7, I could have put 7.9, whatever. So obviously, the x is going to be between what?
2 and 3.
Yes. And probably closer to 2 or closer to 3?
Closer to 2.
Closer to 2. If we look at this log function, right? If we look at the behavior of the exponent, you see it's not increasing that fast, right? Remember, the log is the exponent. So this thing is almost trying to flatten out, right? Almost like a square root function at the end. So it's not going to increase that fast, right? But now, of course, look, when you think about like the Richter scale, which is a logarithmic scale, a 7.0 earthquake to an 8.0 earthquake is not one bigger. It's 10 times bigger, right? Because it's an exponent of a log function, so it's a base 10. So when the Richter scale goes up from 7 to 8, it's 10 times bigger. It's a huge jump, right? So, but if we're looking at this, you can see that when I look at just the exponent, you see the exponent is kind of crawling, right, from here to here. It's not increasing that much, right? So anyway, 2 to the x equals 5. I'm going to choose to get this answer log base 2, right? So I'm going to take log base 2 of both sides. What happens on the left?
It comes out to x.
Exactly. I could say, well, let's bring the exponent out first, and then I get log base 2 of 2, right? And of course, what exponent makes 2 raised to the exponent equal 2? It's 1. So this is all 1. Or I could just say that it's just my plain old everything cancels out, right, when I'm using inverse functions. So I get x equals log base 2 of 5. Now, guess what? I could have just rewritten this. Do you see the translation? Do you see the translation from here to here?
Yes.
Okay.
It's the same thing as
the
very first
translation.
Y.
Yes. So, but I'm going to use this little trick of taking the log of something with a base in mind. So if I have a 2 to the x, I want to use a log base 2 to cancel it. And you're going to see that it doesn't matter if I do that or not, but that's usually the first idea. So, but this one I can't solve. I can't solve this. Well, I do have this on my calculator, but I'm going to use my change of base. So I'm going to use log of 5 over log of 2, or ln of 5 over ln of 2. That's usually my choice, but all of them will work. And so what do we get for our decimal? Ln of 5 divided by ln of 2, 2.3, 2.321928095, where x is approximately 2.3. You get the same?
Yeah, I got the same answer.
Nice. 4, 8, 12, 16, 20. Only missing one student.
So, Professor,
Yes.
I'm a little bit confused as to why you use like a log base 2 to like cancel or reduce stuff down.
Yeah. So as soon as I see my 2 to the x, I know a log base 2 is a good candidate to use. Now, but most of the time I just use ln. So I'm going to show you the same problem with ln. I'm going to take the ln of 2 to the x equals the ln of 5. The x comes out as a multiplier. And now I'm going to divide by ln of 2. So I get x equals ln of 5 over ln of 2. That's typically my choice. Oh, ln of 2. And then I'm to the calculator again.
Okay. I think it makes a little bit more sense now, I think. And then once, like, you have ln of 5 over ln of 2, is that...
That's my exact answer. That's my exact answer.
Oh, okay.
All right.
I thought you could, like, change the base or something.
Or I could change the base, of course. I would like it. I will probably say, give me this answer as a single logarithm. This now I have 2 logs involved. I would like a single logarithm. That would have to be log base 2 of 5, which of course I got in the previous answer. And then of course an approximated answer. So this is exact answer with 1 log. And that's what I'm going to ask for under test.
Okay. All right. That makes a little more sense. Thank you.
Yes. All right, let's go right away to 5.6. And we don't have to, there's no lecture on it because we're just using these properties to find the answers of log equations. And let's just do the hardest one first and see how you do, right? What time is it? 9:39. Oh, awesome. Okay. Oops, let me jump to 5.6 homework. Yes, Alejandra's asking, can I go right to the translation? Yes. In this case, you can. Why I did that work is because that work is what you're going to have to do in the types of problems I'm going to give you. So yes, in that first problem I did, 2 to the x is 5. Could I go right to the translation? Yes. And then change a base, right? I'm sorry, I don't know what the hell's going on here. I hate this book. I'm just trying to open the book again. I don't know why it closes on me in 5 minutes. When you do your write-up for the course, you feel free to let them know how much you hate MathXL.
Oh, I will be doing that.
Good.
They will hear scathing words from me.
Nice. So the ones I really like, these are too easy. What the hell? No, here we go. The ones I really like are like 41 to 56. So let's do number 50. You can't see it yet. I'm sorry. I forgot. So this is a 5.6 number 50, and we'll look at the MathXL ones and make sure there's a couple of decent ones in there for you as well. So I've got 2 to the x plus 1 equals 5 to the 1 minus 2x. And this is a perfect type of problem for me to give you on the test. So probably 2 or 3, and I'll show you the other ones are going to come from so this is an exponential problem, right? And then I'd probably give you at least one with a log problem, right? So this is an exponential problem because as I have exponents, right? And then if you see the word log or log base b, right, that's a log equation. This is an exponential equation. And of course we switch our properties to solve either one. So what log is good here? Besides, well, we know all of them are good, but what looks particularly interesting?
Log base 2.
Sure, log base 2 or log base 5, right? Log base 2 or log base 5. I prefer ln. I just prefer ln, so I'm going to take the ln of both sides. What allows me to do so?
That they have the same base?
Well, ln and ln, yes. But I already know my exponential's 1 to 1, and log is 1 to 1, and so I can compose 1 to 1 functions with each other and keep equality.
Right. Okay.
What happens on the right or on the left? I have an exponent of x plus 1 times the ln of 2, and I have to be careful there that I make sure I wrap my multi-term exponents in parens. And on the other side, I get a 1 minus 2x times the ln of 5. Everyone okay?
Yeah.
What's the purpose of taking a log function of both sides is to get the exponent down, to get the variables down onto the ground, to get them to be coefficients. Because now I just have some algebraic expression, right? ln of 2 is just a number. ln of 5 is just a number. I want to gather all my x terms on one side, right? Just like I've done in the past. So I need to distribute here x ln of 2 plus 1 ln of 2 equals 1 ln of 5 minus 2x ln of 5. Again, I want to gather all of my my x terms on one side, minimizing the number of negatives. So I have x ln of 2 plus 2x ln of 5 equals ln of 5 minus ln of 2, right? Does everybody see what's happened? This piece moved to the right, to the left, from the right to the left and became positive, right? And this piece moved to the right and became negative. When I move a term, switch the signs, right? Everyone okay?
Yes.
Yeah, but why did you switch them? I thought they were.
Remember, I'm trying to solve for x, so I need all my x terms on one side.
Oh, okay.
Yep.
I didn't see the negative 2x.
Yeah.
Excuse me.
So I can factor out an x here, right? I get ln of 2 plus 2 ln of 5 equals ln of 5 divided by 2, right? On that right-hand side, I see I'm subtracting 2 ln's. I can take that argument as a quotient. I can do a little bit more here. I can see this 2 ln of 5 would become what?
ln of 25.
ln of 25, right? There's my 5 squared. I skipped a step there, but make sure you see it. That 2, right? That 2 is a coefficient of an ln, so that 2 can go in as an exponent to the argument. So I get x times the ln of 50 equals ln of 5 halves. Right? 2 times 25 is 50. And so I get x equals the ln of 5 halves divided by ln of 50. Excuse me. That's a very good exact answer. I'm going to ask you to write it as a single log. So we're going to say x equals log base 50 of 5/2. There's my change of base formula. And of course, I'm going to use the previous one to get myself I'm going to use the ln of over ln of to get my approximation. So ln of 5/2 divided by ln of 50, 0.23422422698. So x is approximately 0.2. So one problem just like that on your test. So practice. Practice, practice, practice. Right? It's the algebraic manipulation, but it's almost identical to finding an inverse. So that's good, because if you can find that inverse function, you can do a problem just like this, right? They get a little bit more complicated when I start multiplying things on one side. Like 47 and 48. I'll just show you this real quick. You can take a picture if you want. (47, 48) I like. I like it better with a coefficient, a variable on both sides. So, but all of those, definitely I would say do all of those. Probably all of these as well. Let's pick a couple to do here. Now, the thing about these log equations is I can get extraneous answers. So you're going to have to go back and make sure your solutions that you get are in the domain of the log function, right? So you just have to be careful about that. So let's look at 17, okay? Log of x plus log of x plus 15 is equal to 2. So what are you thinking about? What's your hunch there? This is number 17, 5.6, number 17. Log of x plus log of x plus 15 equals 2. What do you say? What's your gut say?
We can multiply log of x and log of x plus 15.
Exactly. So I get log of x times quantity x plus 15 equals 2. The problem is I got an x inside of my log function and I'd like it out, right? I'd like it to get out of there. So what do? How do I get rid of a log? I use the inverse function base 10.
Use the x base 10.
Yep. So base 10 of log of x times x plus 15 is going to equal 10 raised to the 2. There's the mistake I usually see. I'll see a student raise the left side to base 10, but not the right side to base 10. What happens to 10 to the x and log of x? What happens to 10 base 10 and log base 10? They undo each other, so I just get the argument. And now I'm just doing a quadratic, right? X squared plus 15x minus 100 equals 0. Most of these turn out to be factorable. what is it, 5 times 20? 5 times 20 will get me a negative 100, right? And 20 minus 5 will get me a positive 15.
So when you want to get rid of a log, you do that base 10?
Raise both sides to the base of, yeah, exactly. For a log, it's base 10. For ln, it's base e.
Okay.
And so now I get x equals negative 20 or x equals positive 5. I got to make sure I check these because I could have an extraneous solution. And obviously, it's my negative 20 doesn't work.
And it doesn't work because A can't equal negative?
And I put it back in my original, right? So my first problem says log of x, yes.
Right.
So
right.
I put the negative 20 in there and my calculator went nuts.
Mm-hmm. Okay, got it.
I got to check it in both, everywhere, right? Wherever there's an x. But as soon as it fails for one of the pieces, it fails. So once I saw I would do a log of negative 20, that can't happen. Nice. The rest are very similar, right? The rest are very, very similar. Let's do 32. Log base a of x. So 5.6, number 32. Log base a of x plus log base a of quantity x minus 2 equals log base a of x plus 4. Well, on the left side, I've got a sum of logs, so I could turn that into my product, right? And now I'm arguing that I'm base A on both sides. So yes, I could raise both sides base A and everything disappears but the arguments. But I also know that log is already 1 to 1. So I already know that the insides are equal. I don't even have to do anything. I just can say x, so x times x minus 2 is going to be equal to x plus 4. And it looks again like I have a quadratic, right? So I get x squared minus 3x minus 4 equals 0. And most of the time, these will turn out to be factorable. So I need a negative 4 and a positive 1. And so x equals 4 or x equals negative 1. But I have to check both in the original problem, right? And obviously there's a problem with the negative 1, right? So that's extraneous. They won't always have an extraneous answer. So be careful. Make sure you check them both. They both have to work.
Can you have two valid answers?
Yes.
Okay.
Nice. Let's take a look at the Math Excel homework. See, I think this piece is pretty easy. I think the properties are not easy. because it's just weird.
Yeah, just wrapping your head around the rules of logs is kind of freaky.
And it's about practice. It's just about practice. Once you finally learn that once you finally get the momentum of riding a bike, it's like everything is easy after that, right? Same thing, but you have to practice, right? You have to have someone push you.
Professor, I'm not clear with this. Why the way how x is not equal to x is equal to -1 is excluded from the.
Yeah. So I won't skip the step. I was just doing it kind of in my head. So log base a of 4 plus log base a of 4 minus 2 equals log base a of 4 plus 4. And I can see that I'm not going to get any problem from the arguments. Remember, we know that the domain of logs are positive numbers, right? And you can see that I get log base 8, right? Log base a of 8 equals log base a of 8. So it worked. So that's why this is a good answer. I put it in, it worked, right? It's just like when we were first solving quadratics. Once you get an answer, put it back in and make sure it works, right? So when I check the -1, I get log base a of -1. That's already trouble. Plus log base a of -1 minus 2, trouble, equals log base a of, what was it? I forget. X plus 4? Yeah, -1 plus 4. That's fine, but the other ones are no good. I can't put -1 into log base a. Right? These are bad. Right?
Yeah. So what is this specifically this terminology?
So you're saying why does this happen?
Well, now I came to know that -1 cannot be converted into power 4.
Correct.
Correct. I'm not clear with this terminology. Now I understood that why that happens, and I'm not clear with this terminology.
Oh, yeah. So extraneous. You're not
extraneous. Yeah.
Yeah. It just means when I do the algebra, I get a result, but when I check the result, it doesn't work. So it's an extra heinous answer. Extraneous.
It's a false positive.
Yeah. Well, yeah, sure. And it was weird. I was in the hospital the other day, and they got my blood type, and I couldn't believe that there was a mistake on the document. There was a typo. I can't believe there's a typo on a.
You stop.
I hate how it takes me so long to get I just got
Yeah, he always it goes into a story and it takes me 5 seconds to realize it's a goddamn
it's not until it goes it stopped that I realize what it's doing.
All right, I'm looking at Math Excel homework here. And I'm looking at the homework in homework 25. Oh my God, we got a lot of homework. And I just want to make sure that we try a couple of these. Well, sorry, first one's pretty darn easy. And so what do you think we should do here? Log base 3 of x is 2, right? So this is homework 25, number 1. Log base 3 of x is 2. What do you want to do?
Use the first property?
Yeah, the translation, right? So 3 to the 2 is
Right.
equals x, so x is 9. Tough. Could I have done something else? Well, it's the same thing as raising both sides to base 3, right? 3 log base 3 of x equals 3 to the second power. Log base 3 and 3 cancel, so there it is, x equals 9. So either way is fine. There's lots of ways to do this. It's nice to get a little creative every now and then. To be able to be creative doesn't happen often. Let's look at another one. I mean, this one just looks scary. It's nothing is difficult here. 1/3 log base 4 of x.
Bring the exponents in and then raise both sides to 4.
Yep, 1/3 log base 4 of x equals 2 times log base 4 of 5. Yeah, so bring in the exponents, right? So log base 4 of x to the 1/3 equals log base 4 of 25. Is that okay with everybody?
Yeah.
Once I know I have one-to-one functions here, and I have y values, I know the x values are equal. So I know x to the 1/3 has to equal 25. And then I'm just going to raise both sides to an exponent of 3, right, to get an x equals. So 25 cubed, I think is 625. You better check it. We got to answer low battery. 25 cubed?
25 cubed is
No.
15,625.
Yeah. I was thinking 5 cubed.
I was as well.
Now, is there a problem with this answer? No.
It shouldn't be.
No.
No.
Extraneous.
Right. Easy, right?
Very much so.
Let's hope they have ones that I'm going to put on my tests. They should, because I created these problems. Oh, is that all I get? I'm out? All right, make sure you do those problems from the textbook. I'll see if I can add a couple of problems from this section more equivalent to the test. Okay. Nice. Should we do, let's do a domain problem for logs and then quit, okay? So this is this is the second question on your test. I want to use a sine table to find, oops. Sorry, getting myself seasick here. Use a sine table to find the domain of f of x equals the ln of x x cubed minus 1 over x squared minus 3x minus 4. Everybody with me? Now the first thing, of course, you could do is just graph this function and then use the graph to help you, right? But we know what it's what it means to do a sign table. So we're going to say that g of x is x cubed minus 1 over x squared minus 3x minus 4. And we want g of x to be greater than 0. So we've got to factor g of x completely. We've got to find the critical values, create the table, find test values, and then answer the problem, right? So g of x factors of the top to x minus 1 times x squared plus x plus 1. Anybody need to see how I did that?
Yeah, I would like. Oh wait, no. Did you just factor it out?
I did
Okay.
factor it, but I would say I did it by synthetic division, right?
Right.
I know 1 is a 0 into 1x cubed, 0x squared, 0x minus 1. And you'll see I get the x squared plus x plus 1 there.
Yep. Okay. Got it.
So I got my criticals, right? My critical values are minus 1, positive 1, and 4. X squared plus x plus 1 does not equal 0. I could just graph it and see that. I could put it in vertex form and see that it's got a vertex above the ground and opens up. I could do quadratic formula and show that the roots are complex, right? So I got my criticals, and I know they're untouchable. I can't use negative 1. I can't use 1. I can't use 4. So I'm kind of superimposing my number line there. And those guys will give me my columns. And then my rows are going to come from my factors. And I have 4 factors, right? I've got an x minus 1. I've got an x squared plus x plus 1. I've got an x minus 4 and an x plus 1. And then I'm going to get the g of x out of all of those. How are we doing here? This is the second question on your exam, right? I need test values left of, right of, and in between all my criticals. So I'll pick a negative 2, I'll pick a 0, a 2, and a 5. Anything left of negative 1 will work. Anything between negative 1 and 1 will work. Anything... Yes. Joe?
My bad.
I put those test values into my factors, right? Put the test values into my factors and just find the sign, the SIGN, right? I get a negative, I get a positive, I get a negative, I get a negative. So that piece is underground, no good for me. That piece of g of x is underneath the x-axis, which means they're negative numbers. The outputs are negative numbers. I cannot put those into a log function. I can only put positives. Non-zero, right? No, yeah, positives. Not 0, not negatives. I can't put in. When I put in the, is everybody okay here?
Yep. So you will always look for positives, or it
I need
depends on
the final result to be positive. Remember, I'm multiplying and dividing by these negative terms. So an odd number of negatives will turn out to be negative. So I've got 4 factors in my function and 3 negative terms. So the product will be negative. Plug in the 0, I get a negative, I get a positive, I get a negative, I get a positive, so there's a positive. So I know I want the interval from -1 to 1, because that's a positive, right? It's positive results of G, and then I'm putting them into the ln function, so allowed. When I put in 2, I get positive, positive, negative, positive. So that's negative, so it's no good, right? And then when I put in 5, I get all positives. So I want that interval from 4 to infinity. So f of x equals the ln of x cubed minus 1 over x squared minus 3x minus 4 has the domain -1 to 1 union 4 to infinity. And of course, the graph will verify it, that I have those two pieces that are above the x-axis for g of x.
And if it will be gx less than 0, we'll be looking for that negative.
Exactly, but we can't put the negatives in the log function. So that's a question you would have had, right, in 4.6, right, just to get you ready for this domain problem.
So when we're finding the domain using sign tables for logs, we'll always look for positive.
Exactly.
We're actually finding the sign table for the inside of the log.
Exactly.
And then that's its domain.
Yep. So let me just do that on Desmos real quick, and then we'll go. Okay, desmos.com. So I want to write y equals the ln of x cubed minus 1 all divided by x squared minus 3x minus 4 and you can see there's two pieces where the graph is above ground, right? There are two pieces where the graph is above ground. And we already know that they're between -1 and 1. You can see it, right? I'm sorry, there are two pieces of the function. Sorry, not what I said. So, but if I graph x equals -1, I get that bound. If I graph x equals +1, I get that right bound, and then I'll get a left bound from x equals 4. So you can see where my ln function exists is between those points, between -1 and 1 and right of 4. Now here's the real thing I'm trying to show. The real thing I'm trying to show is what is the look of g of x. I wanted g of x to be above ground, right? ln is not above ground here because ln can give me negatives, right? But it's important that the argument, that what's inside, is positive. So I had y equals just that inside. Let me cheat and just copy it, so not type it again. And
you're getting points off for that.
Exactly. Now look at the pieces where the black curve is above ground. That's what's allowing me the domain of ln in red. Right, so the black curve is above ground between -1 and 1 and right of 4. And that's exactly what I got.